In the steep forest ranges of Oberziering, the Starkholz harvesting process is executed with a high level of technical precision to safely extract oversized, high-value timber. Operations begin with detailed stand assessment, where forestry specialists evaluate trunk diameter, fiber quality, slope stability, and the optimal felling direction. This planning phase is essential when dealing with Starkholz, as individual logs can exceed several tons and demand controlled handling from start to finish. The felling sequence relies on professional chainsaw techniques and hydraulic assistance. Skilled sawyers create accurately aligned notch and back cuts, allowing the tree to fall along a predetermined vector. Stabilization wedges, high-capacity jacks, and safety winches are often deployed to maintain control on uneven terrain. Once the trunk is on the ground, precision delimiting removes branches cleanly without damaging the core timber. This is followed by bucking, where each section is measured and cut according to sawmill specifications for structural lumber, veneer blocks, or long-length beams. Extraction requires machinery built for extreme conditions. Heavy-duty skidders, cable yarders, or tower yarding systems pull massive logs uphill or across steep ravines with minimal soil disturbance. In Oberziering's mountainous landscape, skyline cable systems are frequently the most efficient solution, suspending logs off the ground to preserve both terrain and timber integrity. High-tension wire ropes, remote-controlled carriages, and shock-absorbing braking units ensure steady, vibration-free movement of each Starkholz section during transport. At the landing site, logs undergo further technical preparation. Debarking heads or drum systems remove surface material when required, while laser measuring frames verify diameter and straightness. Sorting cranes equipped with rotators position each log into categorized stacks based on grade, density, and intended use. Moisture checks and fiber inspections help classify premium quality Starkholz, which is later used for laminated beams, bridge elements, or specialty architectural applications. Throughout the operation, strict safety and environmental protocols are upheld. Slope analysis, load calculations, and controlled machine traffic reduce erosion risks. All equipment, from chainsaws to yarders, operates under calibrated parameters to ensure predictable mechanical performance. Continuous communication between sawyers, machine operators, and yarding personnel guarantees synchronized workflow, particularly when maneuvering multi-ton timber in confined alpine corridors. The result is a highly coordinated harvesting process that transforms standing trees into industrial-grade Starkholz, with maximum yield and minimum impact. In Oberziering, this technical mastery showcases how traditional forestry expertise and modern machinery combine to extract large timber safely, efficiently, and sustainably. In an automated sawmill, the production line layout is engineered to maintain continuous material flow, optimal cutting accuracy, and high overall productivity. The process begins at the log infeed deck, where scanners measure diameter, taper, and curvature in real time. Automated feeders position each log onto the debarking unit, ensuring clean surfaces for downstream cutting. From there, logs enter the primary breakdown saw, typically a twin arbor or chipper canter system, which converts round logs into squared cants with precise dimensional control. The cants move along high-speed conveyors to the secondary sawing line, where multi-rip saws and edgers refine the material into boards. Optical and X-ray scanning modules optimize cutting patterns, maximizing yield by adjusting blade positions automatically. Boards then pass through automated grading stations, where sensors and vision systems evaluate knots, moisture, and fiber quality before sorting. Once moisture targets are met, boards enter the planer mill, where thickness and surface finishing are standardized. The final stage features stacking robots, strapping units, and barcode labeling systems that prepare each bundle for shipping. This streamlined layout ensures minimal manual handling, consistent quality, and fully traceable production across every step of the automated sawmill operation. The Kettle Falls lumber mill operates as a fully integrated sawmilling system designed to maximize fiber recovery from ponderosa pine logs. Production begins at the log yard, where incoming loads are weighed, sorted, and processed through a high-capacity debarker to ensure clean surfaces for downstream machining. Logs then move to the head rig, where optical scanners and computer optimizers analyze diameter, sweep, and internal geometry. The head rig performs the primary breakdown, rotating each log for the most efficient combination of opening faces. Sideboards are directed to the edger for precision trimming, while the remaining cant advances to the resaw. Here, secondary scanning determines the ideal cutting pattern to extract the highest value boards before they are routed to the trimmer. After trimming, boards enter an automated sorting line that classifies them by width and length before stacking. Green lumber is stickered for airflow and transferred into one of 6 kilns, where tightly controlled drying cycles, ranging from 24 to 120 hours, reduce moisture content to 12% or less. Once dried, material flows into the planer mill for final surfacing, grading, and trimming. Automated stacking, strapping, and packaging complete the process, ensuring consistent, warp-resistant lumber ready for commercial distribution. A wooden coil-making machine operates as a compact, fully synchronized system designed to shape, press, and finish wooden bobbins with high-dimensional accuracy. The process starts as pre-cut wooden slats are fed into the forming station, where servo-controlled rollers bend each piece into a precise, circular profile. A heated press immediately stabilizes the curvature, locking the wood into its coil geometry while minimizing internal stress. From there, the shaped segments move to the assembly module. Next, a dedicated drilling spindle performs axial and radial drilling cycles based on preset coil specifications. Holes for fastening, alignment, or ventilation are created with micron-level accuracy. Servo-driven positioning tables synchronize every movement, allowing each bore to align precisely with the coil's curvature. Engineered for repeatability and continuous operation, this machine delivers high-quality wooden coils ideal for cable packaging, furniture components, and specialty industrial applications. Steel-wooden cable drum assembly combines robust metal hardware with precision machined wooden components to create a durable spool capable of carrying heavy electrical, fiber optic, or industrial cabling. The process begins with the preparation of the wooden flanges, where each panel is cut, milled, and edge trimmed to achieve uniform thickness and a perfectly circular profile. Automated drilling units create mounting holes that align with the steel center hardware and reinforcement rings. Steel components, including hubs, bushings, and internal braces, are fabricated separately from hot-rolled plate or tubular stock. These parts undergo CNC machining for dimensional accuracy, followed by surface treatments such as galvanizing or powder coating to enhance corrosion resistance. Once inspected, they move to the assembly line, where the integration with the wooden flanges takes place. During assembly, a hydraulic positioning table holds the first flange in place, while the steel center hub is inserted. A precision alignment jig ensures the hub sits perpendicular to the flange, preventing wobbling during rotation. Reinforcement rings are then fitted and secured using high-torque pneumatic drivers. The drum's barrel is formed using longitudinal wooden slats, which are compressed and wrapped around the hub using mechanical clamps. This creates a stable core, capable of handling the compression forces generated during cable winding. After the wooden flanges and the core are positioned correctly, the manual bolting stage begins to complete the drum structure. Every nut is threaded by hand at first, ensuring proper positioning and preventing any misalignment during final tightening. This method ensures even force distribution across the flange surface, minimizing distortion and significantly improving structural stability. During tightening, the technician continuously checks the clamping pressure by both visual inspection and tactile feedback, ensuring every joint reaches the required level of firmness. By combining steel precision with the resilience of engineered wood, modern cable drum assembly lines deliver high-strength spools that support heavy industrial use while maintaining strict dimensional and safety requirements. The assembly of a Matum reel begins with the preparation of its core components, including the steel or wooden flanges, the central hub, and the cylindrical barrel. Each part is first visually inspected for dimensional accuracy and surface quality, before being positioned on the assembly platform. The flanges are aligned with the hub, ensuring the central axis is perfectly straight to maintain rotational balance during operation. Next, the manual bolting process secures the flanges to the hub. Technicians insert each bolt by hand, ensuring proper alignment of the holes, then tighten them in a specific pattern to evenly distribute stress and prevent warping. After the initial hand tightening, torque wrenches are used to apply precise clamping force according to specifications. Once fully assembled, the reel undergoes a rotational check and final inspection to verify concentricity, flange flatness, and structural integrity. Only after passing these tests is the Matum reel ready for cable winding or shipment. Carly Wood Products, operating under the brand Carlamine, is a modern woodworking facility specializing in the production of high-quality laminated and solid wood products. The manufacturing process begins with the careful selection of raw timber sourced from sustainably managed forests. The selection process emphasizes wood species, grain quality, moisture content, and absence of defects, ensuring that only the best material enters production. Once the timber is received, it is sorted and stored in climate-controlled conditions to stabilize its moisture content, a critical step to prevent warping or cracking during subsequent processing. The wood is then cut to size using precision bandsaws and circular saws. CNC-controlled cutting machines ensure accurate dimensions and reduce material waste. For laminated products, boards are planed to achieve uniform thickness, smooth surfaces, and consistent edges. The lamination process involves applying industrial-grade adhesives under controlled temperature and pressure conditions. Layers are stacked according to design specifications, with grain patterns aligned for both structural strength and aesthetic appeal. Hydraulic presses maintain consistent pressure across the laminated assembly, ensuring proper bonding and minimal voids between layers. After curing, the laminated panels are trimmed to final dimensions and sanded to achieve a smooth finish, ready for additional machining or surface treatment. Advanced CNC milling and routing operations are then used to create grooves, dados, and complex profiles. These machines, equipped with multi-axis capability, enable precise shaping for furniture components, flooring, and architectural panels. Drilling operations for dowels, screws, or fittings are performed on automated drilling lines, allowing for consistent positioning and depth control across batches. Surface finishing is another critical stage. Depending on the product line, wood panels undergo sanding, staining, varnishing, or coating, with water-based and UV-cured finishes. Automated spray booths ensure uniform application, while drying tunnels or UV ovens accelerate curing, maintaining dimensional stability and durability. The finishing process not only enhances aesthetics, but also increases resistance to moisture, abrasion, and wear. Quality assurance is embedded at every stage. Visual inspections are supplemented by mechanical tests, including bending, tensile, and adhesion tests for laminated panels. Moisture meters, thickness gauges, and laser measurement tools are used to ensure dimensional accuracy and consistency. Defective components are removed or reworked, guaranteeing that only products meeting strict internal standards reach the next stage. Assembly of finished furniture components follows, including attaching legs, panels, and fittings. For seating products, high-density foam cushions are shaped and then covered with fabric. The fabric is stretched and secured over the seat frame, ensuring smooth, wrinkle-free surfaces. For transport, each upholstered seat is further wrapped in protective polyethylene, preventing scratches, moisture damage, and dust accumulation. The final step is packaging. Panels, frames, and upholstered seats are carefully stacked and interleaved with protective material. Units are banded, wrapped, and labeled according to customer specifications. For export products, additional strapping and edge protection are applied to withstand long-distance shipping. Carlomagne's production facility integrates modern dust collection systems and energy-efficient machinery, ensuring a safe and environmentally responsible operation. This combination of automated production lines and skilled craftsmanship allows Carlomagne to deliver high-quality, ready-to-ship wood products with upholstered components for furniture, construction, and interior design industries, both domestically and internationally. At Sencria Sandali, chair manufacturing is defined by a refined balance of precision engineering and meticulous craftsmanship. The process begins with the careful selection of hardwoods such as beech, oak, and ash, materials chosen for their durability, stability, and elegant grain structure. Each log undergoes moisture testing and surface inspection before entering a controlled drying environment, ensuring that every piece of wood achieves the stability required for accurate machining. The production flow starts with primary cutting operations. Logs are converted into planks using high-yield bandsaws and automated cutting lines that minimize waste. These planks then enter CNC machining centers where legs, frames, rails, and support components are shaped to exact specifications. Multi-axis routers carve contours, bevels, and joinery features with precision, ensuring perfect alignment during assembly. All components are sanded progressively, from coarse to fine grit, until a smooth, uniform surface is achieved. For curved elements, especially backrests and ergonomic seat bases, a specialized laminating process is used. Thin veneer sheets are selected for flexibility and grain quality. Adhesive is applied using automated glue rollers, followed by manual inspection to confirm even coverage. Multiple veneer layers are stacked and placed into forming molds, then loaded into hydraulic presses. Heat and pressure work together to bend and fuse the layers into strong, consistent curves. Once pressed, these laminated panels are sent to curing racks, where adhesives stabilize before trimming, routing, and final sanding. Assembly takes place in a specialized section equipped with precision fixtures. Mortise and tenon joints, dowels, screws, and corner blocks are fitted with accuracy, and industrial adhesives reinforce every connection. Frames are clamped to maintain alignment while the adhesive cures. Seat bases and back panels, both flat and curved, are mounted according to model specifications. After machining, all wooden components move to the finishing line. Automated spray booths apply stains, sealers, and protective top coats in multiple layers. Between each coat, technicians hand sand the surfaces to achieve a flawless finish. For premium models, UV-cured coatings enhance scratch resistance and long-term clarity. Controlled drying tunnels ensure optimal curing conditions and uniform color consistency. A signature highlight of Sankria's process is its handcrafted upholstery. Each piece of leather or fabric is cut, stitched, and refined completely by hand. Skilled artisans sew seams, align patterns, reinforce corners, and create tight, even contours that no automated system can replicate. For leather models, technicians perform edge folding, corner tucking, and decorative stitching manually, ensuring a premium look and long-term durability. Once each cover is completed, Upholsterers stretch it over foam cushions and wooden bases, securing it with industrial-grade staples. Because everything is hand-shaped, every seat fits with exceptional precision and aesthetic consistency. Before packaging, quality control specialists perform structural, load, and stability tests to ensure the product meets Sankria's uncompromising standards. Only chairs that pass every inspection step are cleared for packaging. In the final stage, chairs are fitted with corner protectors, placed in reinforced cartons, and labeled with tracking codes. Palletizing follows export standards, ensuring stability and safety during transportation. Through a fusion of advanced woodworking technology, precise veneer bending, durable finishing systems, and expert hand-stitched upholstery, Sankria Sandelier delivers chairs that embody both engineering excellence and artisanal artistry. At ML Furniture, the manufacturing line operates as a precisely coordinated technical system built around automation, data-driven control, and strict dimensional accuracy. The workflow begins in the graphics and engineering department, where customer requirements are converted into detailed 3D models. These models generate complete process documentation, machining layouts, and CNC programs that guide every downstream operation. An advanced production planning platform analyzes order volume, board utilization, and machine availability, ensuring continuous flow across all production cells. The physical process starts with premium laminated boards, selected for structural stability and surface durability. These full panels move to high-precision CNC panel saws equipped with automated positioning, laser measurement, and intelligent nesting software. Each sheet is cut into accurately sized form pieces, maintaining tight tolerances even at high throughput. Automated stacking systems then collect and organize these components for the next phase. Edgebanding is one of the most technically demanding stages in furniture production. ML Furniture deploys high-speed edge banding lines featuring infrared preheating, EVA or PER adhesive systems, pressure rollers, and multi-stage trimming units. This process seals the most vulnerable area of each component, enhancing resistance to moisture, impact, and long-term wear. The precision of edge application directly influences both structural integrity and final appearance. From there, components advance to CNC drilling and boring centers. Multi-spindle units execute all hinge pockets, dowel holes, connector points, and fixing slots in a single automated cycle. The resulting accuracy allows even inexperienced customers to assemble the furniture with perfect alignment, free of tolerance accumulation or panel mismatch. When non-standard geometries are required, curves, angle cuts, or complex profiles, multifunction machining centers perform routing, contouring, and specialized milling. These flexible platforms allow customization without interrupting high-volume production. Every component then passes through a meticulous inspection stage. Operators verify surface finish, dimensional accuracy, drilling precision, and edge adhesion. Once approved, parts are wrapped according to strict protection protocols to prevent transport damage. Completed packages move into an automated warehouse, where a computerized management system tracks inventory, assigns storage locations, and prepares shipments. Modern logistics solutions minimize delivery time while maintaining consistent distribution performance. Through tightly controlled processes, advanced CNC technology, and disciplined quality assurance, ML Furniture delivers furniture systems defined by mechanical precision, durability, and reliable assembly performance. In precision gunsmithing, the rifle stock is one of the most complex wooden components to machine, combining ergonomic form, mechanical interfaces, and strict dimensional accuracy. On a homebrew 4-axis CNC system, The machining process becomes a highly controlled sequence, where every contour, radius, and inletting surface is shaped by coordinated motion. Although the machine is capable of true rotary interpolation, this operation is performed by indexing the fourth axis, locking the rotary axis at specific angles to complete each machining stage with maximum rigidity. The workflow begins with a fully modeled digital design of the rifle stock. CAM software is used to generate toolpaths that are split into multiple indexed positions. Each position corresponds to a machining zone: top profile, bottom profile, right side, left side, and critical inletting areas for the action, barrel channel, and trigger system. Once the post-processor is fully configured for the controller, these toolpaths will run seamlessly. However, in this demonstration phase, indexing is done manually through preset angle commands. Material preparation is equally important. A laminated hardwood blank is mounted between precise centers on the rotary axis, ensuring alignment along the stock's central datum. The first roughing pass removes the bulk material using an end mill, defining the overall external geometry. After each index rotation, typically 0 degrees, 90 degrees, 180 degrees, and 270 degrees, the CNC executes additional roughing cycles to reveal the final profile. Finishing begins once the global shape is established. Ball nose cutters trace ergonomic curves, grip transitions, and comb radii with smooth, multi-axis toolpaths. The machine then switches to pocketing and slotting operations for the action inlet, magazine well, recoil lug pocket, and trigger channel. Precise depth control ensures proper bedding surfaces and mechanical fit. After the final index cycle, the stock is removed for hand sanding, sealing, and optional glass bedding. The result is a structurally stable, dimensionally consistent rifle stock produced with the accuracy and repeatability made possible by a well-calibrated 4-axis CNC platform. The CMS-R's 5-axis CNC machine is one of the most advanced woodworking solutions for architectural components such as volutes, spiral handrails, and stair treads. Designed with a rigid gantry structure and a fully articulating 5-axis spindle head, ours enables the machining of complex geometries in a single setup, minimizing errors caused by multiple repositionings and increasing repeatability for twisted or curved parts. The machining workflow begins with creating a 3D model of the volute or stair tread in CAD/CAM software. Engineers then use specialized CAM tools to generate 5-axis toolpaths covering roughing, semi-finishing, and finishing, ensuring that the cutter always approaches the surface at the optimal angle, reducing tool load and preventing collisions. The wood blank, typically solid timber or laminated hardwood, such as oak or ash, is placed on the multi-layer vacuum table or on dedicated fixtures of the Aries system. The integrated probing unit scans the surface to establish the workpiece origin, compensate for material deviations, and synchronize the real geometry with the digital model. During roughing, the high-power spindle, up to 12 kW depending on the model, uses aggressive milling cutters to remove large volumes of material quickly. Thanks to 5-axis motion control, the tool maintains the most favorable orientation, reducing deflection even when cutting boards with twisted grain or curved laminations. Semi-finishing uses smaller cutters to refine curves, channels, transitions, and compound surfaces. Continuous 5-axis interpolation ensures smooth, flowing profiles, an essential requirement for volutes or spiral handrail elements. Final finishing is performed with ball nose tools, delivering a clean surface that often requires little or no manual sanding. The machine can also perform drilling, slotting, and mortising through its multi-axis drilling and routing capabilities. Joint holes, rail connection slots, dowel positions, and screw holes can all be machined in the same cycle, reducing the amount of manual assembly work required afterwards. To maintain a safe and clean workspace, CMS Aries is equipped with a high-efficiency dust extraction system. This setup captures chips and fine dust directly at the cutter, ensuring cleanliness, protecting the operator, and preserving machining accuracy. Aries also incorporates CMS adaptive technology, an intelligent CNC control method that optimizes material removal on complex surfaces without compromising finish quality. As a result, curved and spiral components can be produced faster, while maintaining high-dimensional precision, providing exceptional tool accessibility from multiple angles. The spindle reaches speeds up to 24,000 revolutions per minute, enabling high-speed cutting and fine finishing on wood and composite materials. Aries machines generally use FANUC CNC control systems, featuring a multilingual interface, large display, and network-based data storage capabilities. The work table can be configured in standard large format or pendular mode, allowing alternating loading/unloading to maximize production efficiency. A standout advantage of the system lies in the B and C rotary axes, which make it possible to machine spiral curves, volutes, and stair components that are extremely difficult, if not impossible, to produce on conventional 3-axis machines. Combined with multi-directional tool orientation, Aries can create seamless handrail and stair elements while reducing the need for manual craftsmanship. In summary, CMS Aries is a high-performance CNC platform purpose-built for architectural woodworking, volutes, spiral handrails, stair treads, and decorative curved components. Its combination of a rigid mechanical frame, flexible 5-axis spindle, adaptive material optimization technology, and advanced dust extraction system delivers a powerful, precise, efficient, and production-friendly machining solution. The Holzherr Multirex 5-axis CNC machining center represents advanced, high-performance capabilities for solid wood and panel woodworking, especially in applications like stairs, windows, and doors. Its robust industrial gantry design supports dynamic 5-axis interpolation, enabling the machine to mill complex geometries in a single setup without repeated reclamping. Engineers begin by defining the part in CAD/CAM software. From there, the CAM system generates multi-stage toolpaths, roughing, semi-finishing, and finishing optimized for 5-axis motion. This strategy ensures the cutter approaches every surface from the best angle, minimizing load and avoiding collisions. The integrated probing system scans each part to locate true zero and compensate for any dimensional deviations, ensuring perfect alignment with the digital model. During rough machining, a high-power spindle removes material aggressively. More advanced versions use a spindle with axis locking, which increases torque during heavy cut loads. In semi-finishing, continuous 5-axis motion refines curved surfaces. Final finishing is done with multi-axis interpolation, leaving smooth surfaces ready for sanding. Additional functions include drilling, grooving, and mortising in the same cycle. This allows dowels, hinge pockets, and connection slots to be milled precisely without separate setups. To maintain a clean workspace, the Multirex features integrated dust extraction right at the machining area, which captures chips and fine dust during operation. Overall, The Holzer Multi-Rex 5-axis CNC machine delivers a powerful, precise, and flexible solution for industrial wood manufacturing, especially when handling long, curved, or highly variable parts in stair, window, and door production.